Hello guys, welcome to Physics Grad. In this video, we are going to talk about the Lagrangian for a system of particles. Okay, and we are going to consider the case where these particles are going to have some kind of interaction with one another. Okay, so let's begin. So first, let's consider. Okay, so consider a system of particles which are interacting with each other but with no other bodies. Okay, so system of particles interacting with each other but with no other bodies. So what do we mean by this statement? So we are going to have some set of particles, okay, and some other set of particles, but what this statement means is that I am going to consider a particular system wherein the particles which make up the system are only interacting with the particles only inside this system and not outside. This means that the particles are going to have interactions only with the particles inside the system, that is with each other, but not outside. So there is no interaction between this particle and this particle, or this particle and any of the particle considered inside the system. Okay, so such a system we will call it as closed system. So a closed system will consist of particles which interact only with other particles inside the system but with no other particles or bodies outside the system. Okay, and we have already seen from our previous lecture that for non-interacting particles, okay, we had seen that the Lagrangian was given by just half m times v square, okay, where v is the magnitude of the velocity of each of the particles, and the summation comes from the additive property of the Lagrangian, okay, which we have also seen in one of the previous lectures. Okay, so this is for non-interacting free particles. Okay, now what if the particles are interacting? How do we introduce this interaction into the Lagrangian? Okay, so how do we introduce interaction term in the Lagrangian? Okay, so to answer this, we need to first describe what do we mean by interaction. Okay, so how do we describe this? That is the first question that we need to ask. So we know that when you have no external influence on the system, the particles which constitute the systems are going to interact with each other via either, let's say, the Coulombic interaction or gravitational interaction and so on. And all of these types of interactions are non-contact interactions, or they come under something known as action at a distance forces. Okay, and all of these kinds of non-contact forces are represented by making use of fields, and these fields are in turn defined in terms of the potential functions. Okay, so we are going to be, so here there is no physical contact between the particles, but in spite of that they interact with each other. So this is a form of what I would like to call non-contact interaction, right? And these arise due to either the Coulombic interaction, gravitational interaction, and so on. So these interactions are usually described by the notion of fields. And these fields in turn are described using something known as the potential functions, right? So we describe them using potential functions. So what are these potential functions? So these action at a distance forces like gravity or Coulombic forces are always dependent on the position of all the particles. They are not dependent on the velocity or acceleration and so on. They are just dependent on the position. So this is going to be just a function of the positions, okay, positions of all the individual particles. So it makes sense to describe the Lagrangian. So we are going to guess the Lagrangian to have the form summation mi vi square plus some function which is only dependent on the position. Okay, so r1 r2 dot 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 till ri. Okay, ri is the general position dot 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 dot. Okay, fine. Now what does this Lagrangian imply? This implies, if we describe the Lagrangian in this form, it implies that the change in position of any particle, okay, so by saying that the potential is only dependent on position, okay, this implies that change in position of any particle, right, will instantaneously affect or influence the other particle. So it will instantaneously affect the other particles. This means that there is no delay when a particle moves, and the information that the particle has moved is in turn seen by the other particles because of the potential change, right? So therefore this particular form of the Lagrangian will not be valid if we consider Einstein's relativity relativistic terms, right? So we are only going to follow Galileo's relativity, at least for these classical mechanics series, and therefore this is going to be a non-relativistic case. So non-relativistic in the sense Einstein's relativity. So this Lagrangian is true for, so this is true for non-relativistic case, and by relativity I am talking about Einstein's relativity. So that's the special theory of relativity, okay, because if we assume that there is a finite delay in the effect of change in position of any one of the particle, it means that this delay implies that this effect is going to be propagating with some certain velocities, and by relativity it is true that with different frame of references these velocities will be seen differently, and which in turn implies that the effect will be different in different frame of references. But that is not true according to our Galileo's postulate, which we are going to follow here, according to which in all the inertial frames the mechanical effects of change of position of particles must remain the same. Okay, so this is a consequence of t dash equal to t in the Galileo's relativity transformations, right? And therefore, by assuming that it depends only on position, it means that change in position implies that the effect of this will be seen instantaneously by all the other particles. There is no delay in other particles experiencing the change in position of any other particle. Okay, and therefore this Lagrangian is valid only for non-relativistic case, and by relativistic I mean Einstein's relativity theory. Okay, so that's cleared up. Another thing that you can notice here is that this Lagrangian is independent of time. Okay, so what is the consequence of this? So its consequence is that the system doesn't know whether you're moving the time forward or backward. So system doesn't care whether time is moving forward or backward. In both the cases, the Lagrangian remains the same. So this means, okay, what does this mean? This means that there is no change in the mechanical behavior if the time is reversed. Okay, so this implies there is no change in the mechanical behavior if t is replaced by minus t, or in other words by reversing the direction of time. So therefore the reverse motion is also possible. So what we mean by this is that if you consider, for example, so if you consider a projectile motion, say, which goes like this, this is how the motion will look if time is running forward. But if you reverse the time, then it will look as if everything is opposite. Okay, so that is the meaning of this this particular statement. Okay, and it is a consequence of the fact that the Lagrangian is not dependent on time. Okay, so therefore all motions which obey the laws of classical mechanics are reversible with respect to time. Okay, so therefore all motions which obey the laws of classical mechanics. By classical mechanics, what we mean is that we are not going to consider special or general theory of relativity. That is the meaning. So classical mechanics are reversible. Okay, so the reverse motion is also possible if we reverse the time. Okay, now let us see what is this function which depends on Ri, R1, R2, Ri, which is basically the positions. So if you observe, we have the Euler-Lagrange equations, which says that the total time derivative of dou L by dou Vi will be equal to the partial derivative with respect to the corresponding position vectors, right? So we saw from our previous video that this will turn out to be mi times dvi by dt because of the half mivi square term. This will be equal to, so here the L is also dependent on some function which depends on the position, so this becomes dou f by dou ri. Okay, so that is basically differentiating this. Okay, but this is clearly miai equal to dou f by dou ri, but miai is basically the force on the ith particle, right? But we know from Newton's laws and by definition, so by definition we know that Fi is defined as minus dou u by dou ri, right? So what is this u? This u is actually the potential energy. Okay, so this is by definition. So force on along a particular direction, so in this case if we consider force on a particular ith particle, then it is equal to negative of the gradient of the potential with respect to the position of the particle. Okay, so this actually gives the field, which is defined as the force acting on a test particle. Okay, but more on that later. So so this is actually proportional to the field. Okay, so this is by definition, and therefore if we compare these two, we see that F must be equal to minus u, and of course this potential energy is actually a function of all the positions, not just Ri, all R1, R2, dot dot dot. Okay, and from this we can say that the Lagrangian is defined as half summation half mivi square minus u of r1 r2 dot dot dot. Okay, so this is obviously called the kinetic energy term, and this is the potential energy term, and if I denote this as by a symbol T and this by a symbol U, we immediately see that the Lagrangian is of the form T minus U. Okay, all right. Now one more thing that we notice here is that the potential energy, how do we define where the potential energy is zero? In fact, we know that L dash defined by L plus some constant C are both equivalent. Therefore, we can say that our potential function is defined up to a constant. What I mean by this is that even if we have u dash equal to u plus some constant C1, then if I have the same thing in the Lagrangian will just have this form, and we know that we will get back the same equations of motion. So how do we define or how do we set this constant C1? So a good way to do this will be to set a reference. Set a reference as u equal to 0. but what will this reference be? Okay, and the most reasonable argument will be from the fact that when all the particles, so when all the particles are infinitely far away from each other, will imply interaction is zero. Because they are infinitely far, it's as if they will not know that there are other particles around them, because the other particles are infinitely far, so interaction will be zero. So we can set this as a good reference point. Okay, so we can set this condition as u equal to 0. So the potential function can be defined in such a way that u will be equal to 0 when all the particles are infinitely far away from each other, and when they come close together, okay, so when they come close together like this, it will be dependent only on the positions of each of the particles. Okay, all right, so that's it for this video. See you next time.